So today I present to you our architecture for experimenting with aerial drone applications. So it all started with an oil company that asked us to, oops, I'm sorry. All right, never mind. Let's go with this. Who asked us to develop an application for examining internals of the oil oil tanks. I'm sorry, I'm missing one slide here. This is probably because I was transferring my presentation from one laptop to another. But never mind. So we immediately thought, so this is the oil tanks are a hostile and GPS denied environment. So we immediately thought about the drones and visual-based navigation inside the tank. So we go with this visual-based SLAM, simultaneous localization and mapping, and we immediately started having problems with that because the existing approach wasn't tuned for the specifics of the oil tank's internals. And we spent a grand amount of time and efforts, and the drones as well, trying to tune this existing SLAM approach. And this is just a mere example, and what we usually face is when we want to deploy any real-time, real-world drone application, we have to always customize the existing approaches and tune the parameters for our algorithms for the specific needs at hand. We could have used simulators for that, but the problem with simulators is that they often oversimplify the drone models, and the parameters we could achieve from the simulators are not optimal enough, if realistic at all. On the other hand, there are test beds that operate with real drones, right? But the problem here is that the applications that they focus on are never intended to move outside the test bed. And in our case, what we need is to experiment on the application level and then seamlessly transfer to the real world. And this is exactly what we focus in our architecture we call FlyZone. So we provide means for application level experimentation and seamless transfer from the test bed to the real deployment. We also provide means for simulation of the external forces, real environment. This could be useful when you decide to test your application inside in a safety environment before you are throwing out your drones out there to the hostile environment. And finally, we provide an API where you can actually define simulated obstacles or safety constraints, which is again useful for obstacle avoidance testing, experimentation, and testing against the continuously changing regulations with the drone flying. And we deliver these benefits with three main contributions. First off, we actually deliver the architecture that you can take away, tune it to your needs, and then deploy in your own place, own location. And yes, we can actually make the drone behave as is it is subject to the external forces, like wind, for example. And finally, we provide our own visual-based localization technique, and I will tell you later why hell we need yet another visual-based localization technique. So there are two main platforms the drone is operating on. First one is using a ground control station, and another one is using companion computer that is usually mounted on the drone itself. And FlyZone aims to both of these platforms, and we also decouple the testbed infrastructure for the actual application you experiment with. So we deploy a drone controller on top of the drone, and it connects to the drone autopilot through a simple UART interface. And it communicates with the FlyZone software and with experimental script. And this script has only one entity per run, and it allows developer to define a multi-drone control, obstacle simulation, and external forces simulation. And when it comes to the environmental influence, the external forces, the whole magic happens inside the FlyZone software. And there are two main problems that we solved here. First off is, how do we create commands so that the drone behaves as if it is subject to external forces? And second, when we have two sources, FlyZone and autopilot software, application-specific autopilot software, how do we deal with the interleaving of those two commands? We have all of this in the paper, but for the sake of time, I will just focus on the first one, how do we tune those commands. But before coming there, we have to understand what physical model should we use before we go to the drone control. And here we have two options. First one is we use a simple model where we represent the drone as just as a dot with a given mass. This is super simple, but on the other hand, it's super inaccurate, and I will tell you later how inaccurate it is. Alternatively, we can use a more detailed model where we represent the drone as a 3D object. This is super accurate, but on the other hand, we have to estimate parameters for that model. The good news is that dozens of parameters already estimated for you online, and if you're lucky, you can find the parameters for your own drone model. If not, you have to do it manually. Once we define what model should we use, we can now see on the basics of physics. When we understand how do we calculate the instantaneous instantaneous change of the velocity and the drone, and we can control it. Here, three values, they are the function mass, its momentum, and the here do the simulation. So we can simulate the speed that is required, speed change that is required to simulate this movement as the drone is, as if it is subjected to the external forces. So this force, combination of forces, is a function of three different types of forces. Gravitational force, which is straightforward, force that is generated by the motors, and again we can calculate it at runtime. This one, we can calculate it at runtime because it depends on the motor modulation, and we can see it programmatically. And the drag force is kind of complicated stuff. We represent it as a force matrix. It's a two-dimensional array where each element is a force with its direction and a strength. For example, we can take an example as a wind map, for example, right? That we can take from the QG software. And then we use it to simulate our external forces. So now about the localization. Why would we need another localization technique? A critical role when it comes to the obstacle avoidance or drag force compensation. And in order to decouple the testbed infrastructure from the application itself, we should not rely on any of the application-specific localization techniques, such as ultra-wideband or visual SLAM. And that's why we provide our own technique that runs in parallel with experimentation. And this is a kind of hybrid technique where we use both visual-based means and readings from the drone sensors. So to get the altitude of the flying, we use this altimeter that is on each drone. Actually, you can find something similar. And then we attach the camera to the bottom of the drone. And this camera points down and reads the two-dimensional tags. And these tags were specifically designed for simple identification and reliability. So here we have a number of tiles, colored tiles per tag, And we have one-to-one mapping from color to number. So if you start from the bottom right tag and go clockwise, you will get a number which is unique for the given tag. And this style over here is shifted for purpose so that the decoding algorithm doesn't depend on the tag. We can so the problem we solved is first, what is these tags. So to understand tiles per tag can we use, and this is non-trivial task because it dimensional area you want to cover. It depends on the camera. And we solved it in our work, and we come out so managed to reduce. And if you want to deploy it on your location, you just can take our formula, put your initial variables in there, and you will have the solution. Next, what we had to solve is how do we distribute the tags on the two-dimensional plane. And this is yet another optimization problem, because what we aim here is to have the tags as different from each other, from the neighboring tags, as possible. And I'll tell you why. Because let's say the camera fails to recognize this color over here, yellow, let's say, which means that all the 6 tags that contain this color here will be incorrectly recognized. Our algorithm can deal with that, so we can filter them out, but how can we get the location? So we still have a chance to extract the location from those tags that don't have this yellow color. So we call it color distance, and we have to maximize it. And yeah, again, we solved it. We provided steps that you can follow to solve it as well. And finally, we incorporate drones readings from the drone sensor to understand what is the projection of the drone center of mass to the frame, because the frame is getting morphed when the drone moves. So overall setup here in our lab, overall setup costed 2,500 euros, which is quite cheap for these kind of systems. And we think that this is almost the same amount you would spend on this testbed, because the main money was spent on this Intel Xeon server. But how realistic it is? So we answered to this question after more than 400 hours of experiments and analyzing over 100,000 of data points. So here, what we aim to achieve is to understand how realistic our simulation is. And before coming that, we have to understand how do we obtain the ground truth for the environmental influence. So for that, we deploy wind machines that create some particular wind configuration. And we measure this wind configuration with digital anemometers. They basically create a two-dimensional wind map similar to those that I've shown you earlier. Sorry. Then we remove these anemometers and we put the drone in there. And we run a simple trajectory like circle and track this trajectory with FlyZone disabled. So, and this is how we obtain the ground truth. So this is the trajectory that drone makes under the when being subject to the external forces like wind. Next, what we do, we remove wind machines and enable FlyZone that incorporates the wind map we obtained previously. And we run this experiment again. So now what we see is the result of the FlyZone simulation when the drone flies not being subject to the wind, real wind, but its behavior is simulated by FlyZone as it is subject to the wind. And so eventually we take these two trajectories and we compare them. So what you can see here, so we actually did it with 3 applications. First one is simple trajectory with application-specific compensation. What that means is when applications see that the drone doesn't follow the given trajectory, it tries to recalculate the trajectory. So it moves the drone back to its trajectory reactively. Second application is trajectory simple, but like circle, but without application-specific compensation. So it doesn't try to get it back to the trajectory. And the simple search is just a path, like follow from A to B to C to D. And as you can see here, all these applications perform similarly, and we see that first off, the FlyZone quite realistically simulate the external forces, and second, the error is not more than 20 centimeters, which is comparable to the size of the drone. It's also comparable to the existing localization techniques like ultra-wideband. I've also compared how different physical models perform, and we see that approximate, when we treat the drone as a dot with the given mass, becomes fairly unrealistic with the increasing wind of speed. Speed of wind, sorry. Next, we tested our localization technique, and so we used OptiTrack system as a ground truth, and we compared FlyZone with the closest counterpart called April tags, and we see that FlyZone performs similarly or better than the tags, April tags. Also, we aim a multi-drone scenario here, and the frame of the camera could be partially occluded, and again we see that FlyZone tags operate better than April tags. When it comes to the performance, we see that FlyZone tags from 2 to 3 times faster, regardless of the platform it's running on. And this is again a result of our design. So we aim to do this. But these are just experiments. What about the real experience? So coming back to our oil tanks, we just needed 5 days to find the optimal SLAM coefficients. And also our gradation students enter the Texas Instrument Innovation Challenge when they develop their obstacle avoidance algorithm using our FlyZone. And finally, we got volunteers that used FlyZone for developing search and rescue application. So we had 10 teams. 5 of those who used FlyZone were able to provide application that finishes faster than those who used ArduPilot, a SciTL simulator, to find optimal parameters for their search and rescue algorithm. So this is how FlyZone actually, what is interesting here is that one of the team provided a solution where a drone wasn't even able to finish its task. This is how FlyZone helps you, help those students, it helped us, and will help you if you deploy it in your own location to find optimal parameters for your application. So thank you very much for your attention, and I guess this is the time for questions.